Now we get into something very specific called the alpha carbon chemistry. You know all about the functional groups, but alpha carbon chemistry is very specific to carbonyl compounds. So let's look at the alpha carbon then, all right? And the alpha carbon is the one that is next to the carbonyl carbon. Here's the carbonyl carbon, here's the alpha carbon, here's the beta carbon. Any proton on the alpha carbon is going to be acidic. Any hydrogen on the beta carbon is also going to be acidic, but if you look at the pKa's, it will tell you that the alpha carbon hydrogen is a lot more acidic than the beta carbon. And the reason for that is polarity. The carbonyl carbon oxygen over here, this bond is very polar, and so due to inductive effect, this bond becomes very polar. So if the carbon-carbon bond is very polar, it makes it easier for this hydrogen to go away. That polarity and that inductive effect decreases as you go farther away from the carbonyl carbon, and so the beta hydrogen is not so acidic anymore. Okay, so because of this acidic nature of this proton, we have this whole other chemistry called the alpha carbon chemistry. So which means that if you have a strong base and you remove this proton, or which abstracts this proton, the proton is going to leave with its electrons on the carbon over here. So which means that you get this kind of an anion, okay, the carbon anion. This carbon anion can now undergo resonance because of the carbonyl double bond here. So the electrons move to the carbon-carbon, and then electrons move from the double bond to the oxygen, giving this kind of an oxide here and the double bond here. Well, these two resonance structures are not just resonance structure, they're called tautomers because you can actually isolate both of them. One of the characteristics of resonance structures is you cannot isolate anything. They're only on paper. They are proven only because of their double bonds or their bond lengths and bond strengths. However, the ketos and the enol tautomers, as they're called, these two can be isolated. That's why they have their names also, and that is why it's a very specific kind of isomerism called keto-enol tautomerism. And this is what happens. So when you have the carbonyl with the double bond, this is called a keto tautomer. And here, this one with the carbon-carbon double bond is called the enol tautomer. And the enol is because there is a double bond over here, which is like a carbon-carbon, so like an alkene. And then this one, if you protonate this oxygen here, then it will become an alcohol, and so this becomes an enol. So these are resonance stabilized. However, you can isolate them, which is why they're called tautomers and not just resonance structures. However, you will show them by this arrow over here, which is a double-headed arrow for resonance structures. Okay, and so this is called keto-enol tautomerism. So this is kind of what happens. Okay, this is how you isolate each of the keto and the enol form. So here comes in a base, abstracts a proton. The proton leaves with its electrons here. So once you form an oxide, and this is the enol, okay, and in the enol, this is what happens, and the oxide will pick up a proton from water and then become alcohol. So this is the enol tautomerism. Okay, now the thing about the keto-enol formation is that it can also happen in acidic conditions. All right, and so you can take the same kind of a carbonyl, and in presence of an acid, the oxygen now will go ahead and protonate, giving this oxonium ion, and then the water will abstract this proton, and then this is the enol that you get. So what happens in these two cases is that you're losing your carbonyl. You still have the double bond, but you've changed the location of the double bond because of presence of a small amount of acid or base. Okay, acid or base. So it changes the location, and if it changes it, then you start getting different kinds of compounds. And these are called enols because they are coming from the carbonyl. However, they're not really carbonyl anymore. Okay, and so these do exist. What it also tells you is that the carbonyl compounds are very acid and base sensitive. So which means you have to store them carefully. You have to be careful how you use them, because a little bit presence of acid or a base is going to create this kind of a tautomerism and this kind of a reaction in them. Okay, and so you can get enols. And the other thing I want to mention over here, I'll probably bring it up again, but if you have a chiral carbon over here, all right, which has this acidic proton, which means the alpha carbon is chiral, then by the time you get to the enol, you've lost that chirality, because once the proton is gone and you have a double bond, you don't have the chiral center anymore. So when you form the keto again, which this is all reversible, so once you form the keto again, will you get the same kind of chiral carbon anymore? No, probably not. So if you started with R, it's very likely that by the time you come back with the equilibrium, you might have a mixture. So you might have a racemic mixture at the end. But anyhow, these keto-enol tautomerisms can happen in both acidic and basic conditions. So here is a specific example of the loss of chirality, okay, during keto-enol tautomerism. So here, for example, is a carbonyl compound where you have one alpha carbon. The other side of the ketone is a phenyl ring, so of course you don't have any alpha hydrogen here, which means that you're looking only at this carbon here. And so once you look at this carbon, here is your acidic proton. So what happens in presence of a little acid or a base, this is what you get, okay, which is actually a plus or minus, which means that you actually have a racemic mixture of the initial compound, okay. And really what happens in the middle is that this proton is going to lose, and therefore you will end up getting this kind of an enol. So this proton, because of this acid or base, is going to transfer to the carbonyl oxygen. And so once it goes there, you end up getting a double bond. Once you get a double bond, then that can go back to the ketone. But then how will you get your proton? Where will it attack? You never know. And so therefore you end up getting a racemic mixture. Now this is something that you really have to be careful of when you're trying to make very specific compounds like medical drugs, because then you have to be careful that if you lose your chirality, then you may actually lose drug activity. So you have to be very careful if your compound is chiral and that's the only one that is going to be active in a system, then that's the only one that you want. So which means you don't want acid or a base, or you want to make sure that you don't have any alpha hydrogen in there. Here are some pKa's for carbonyl compounds, and I just want you to compare a little bit, okay, and see what makes a proton a good proton. So for example, carboxylic acid, the pKa will be very small, obviously, because you have two polar groups, and which makes this hydrogen very easy to go away. And then over here where you have the CH2, this is between two carbonyls, and because of that, this proton is very acidic, all right? And so the pKa is very low. And then it goes on, and so there are some, just compare all of these pKa's, go through it, and you can see how the acidity will keep changing as you change the functional groups, okay? And so by the time you come to something like an amine, you have such a high pKa, it's not even an acid anymore, all right? And then the amides are not very acidic either, okay? And so when we talk about alpha carbon chemistry, we really limit ourselves to esters, and we limit ourselves to aldehydes and ketones, okay? We hardly talk about nitriles or amides or even acid chlorides for that matter, okay? We limit ourselves to again, esters, aldehydes, and ketones. That's what we'll talk about, because then if you have bases and if you have an acid, then you will have your traditional acid-base reaction with this proton and not with the alpha proton, okay? Because if you compare the acidity of these two protons, then the acidic, this proton connected to the oxygen is way more acidic than the one connected to the carbon. And so if a base comes around, this proton is going, not the alpha carbon proton. So you have to be able to decide which proton to pick, and that's why this table is here, so you can get an idea of the pKa's and how to determine which proton is going to be more acidic. So what kind of bases do you use for this? Do you use sodium hydroxide? Do you use butoxides? What do you use? So you really have to be very good in choosing your base. You don't want to use something that is a good nucleophile, because if you have a good nucleophile, then that will actually do an addition to the carbonyl carbon. We've done all the nucleophilic addition on carbonyl carbons back in the aldehyde and ketone chapter, and also in the esters chapter. So you really don't want a good nucleophile. You really want a good base, because bases abstract protons, whereas good nucleophiles will go to electrophiles, which is the carbonyl carbon. So you don't really want a good nucleophile. So a good base is going to be a sodium hydroxide, which is very traditional to use for these kind of reactions. And the other one is the lithium diisopropyl amide, which is called LDA for short. And this is the structure. So if you see LDA or sodium hydroxide, then you should understand that we're talking about the alpha carbon chemistry. And then of course you already know your nucleophiles from aldehydes and ketones chapter. A little bit about the stability of the keto-enol tautomers. Now, since they're tautomers, which means that you can isolate both of the forms, the keto and the enol form, it is very likely that one of the tautomer is more stable than the other. Okay, and so it depends sometimes on the conditions, whether you have acidic or basic conditions, and sometimes even without acidic or basic conditions, you may actually have compounds that exist in the keto form or the enol form. So for example, if you look at acetaldehyde, which is this one, this is the keto form, and I know it's an aldehyde, but we'll just still call the keto form. And then here is the enol form, okay, for the acetaldehyde. However, it is noted that the acetaldehyde stays more in the keto form than in the enol form. It is more stable when the carbon and oxygen is double bonded rather than the carbon-carbon is double bonded. Okay, so the keto form is a lot more stable, and the same thing goes for acetone. So for example, if you go in the lab and you pick up a bottle of acetone, this is what you're going to find. You will not find the enol form. Okay, however, if you add a little acid or a base to the acetaldehyde or acetone bottle, things are going to be slightly different, but just by themselves you will find them more in the keto form. However, a compound like this, okay, which if you remember, in this case there are two kinds of protons, this one and this one. All right, this is a symmetrical compound, so these two methyl groups, they are exactly the same. So between the CH3 and the CH2 protons, the CH2 are going to be more acidic because they're in between two carbonyls. So in this case, the situation is slightly different. The enol form is a little bit more stable, and it is more stable because it ends up forming hydrogen bond like this in the enol form, and it forms this kind of a cyclic structure, and you know that six-membered rings are very stable. So once you have this kind of a cyclic structure, it kind of stabilizes the enol form a lot more than the keto form. All right, and so the enol form is a lot more stable here. But for small molecules, it's very likely that you will find them only in the keto form and not in the enol form. Let's look at the reactions now that you can do for the alpha carbon. There are a few reactions that are very common, and this slide actually has two of those reactions, alpha alkylation and alpha halogenation. So once the alpha proton has been abstracted by a base, what you generate now is actually a nucleophile. Once a nucleophile has been generated, you can do any kind of substitution reactions with that. So the first one here is alkylation. So once the nucleophile is generated, you can use any substrate. And again, this is just an alkyl halide, and you can take that nucleophile and do an SN2 reaction on this. So you end up forming a carbon-carbon bond, which is really a nice way to add more carbons to your ketones, okay? Which is really, you know, the nucleophile is not adding on the carbon, it's acting on another carbon, all right? And so it's a good way to elongate the chain. So that's an alkylation. And then halogenation is when you can take the alpha carbon and you can add a leaving group to it, like any kind of halogen, bromine, iodine, chlorine, whatever you want. And so here we have the alpha carbon, and in presence of acetic acid, acetic acid is not even that strong of an acid, and you take bromine with that, and you can do an alpha bromination on this. So it's a really good way to add a leaving group now to your compound, okay, which would not have been possible before, but now you can, okay, because you know that these protons are acidic. This reaction, by the way, is the basis for the iodoform test, okay, which is on the next slide. So I'd mentioned the iodoform test to you way back when we were talking about aldehydes and ketones, and I said to you that for methyl ketones, iodoform is a good test to identify, okay, if you have methyl ketones in there or not. So you can differentiate between an aldehyde and a methyl ketone using the iodoform test. And the way it works is that if you take any methyl ketone and then in presence of a strong base and potassium iodide, the methyl ketones will give a positive test, okay, which is a yellow precipitate, and that is called the iodoform, okay, just like if you have CHCl3, it's called chloroform. If you have 3 iodines, it's called iodoform. So anyhow, this is the reaction that actually happens, all right? So you have the hydroxide, and one by one, the protons, okay, will be taken away, and so you end up getting 3 halogens, okay? This already, the way this reaction is starting is already halfway there. So the base, all the protons, all the alpha protons have already been replaced by halogen, which is iodine over here. And then in the last step, okay, what happens is that the hydroxide, the strong base that you use, which is usually potassium hydroxide or sodium hydroxide, this bond is going to cleave and you end up getting an acid, and you get the haloform, okay, which is like chloroform. So you end up getting this, and this is so heavy because of the iodine in there that it ends up getting a precipitate, or it's a solid in nature, and it's also yellow in nature. So it's really very pretty test to do to figure out if you have methyl ketones or not. I also brought this reaction up in context of oxidation, okay, and this is not really the best way to oxidize ketones, okay, but you can oxidize methyl ketones this way. Ketones generally cannot be oxidized with your traditional oxidizing agents. You need special oxidizing agents to oxidize ketones. Aldehydes can be oxidized easily, but not ketones, all right, and so for methyl ketones, however, this can be a way to oxidize, because here is your carboxylate ion, okay? The only thing you have to remember when you do this kind of an oxidation is that you lost 1 carbon, okay? And that's going to happen because ketones are internal groups. So obviously when you oxidize them, you're going to have to break some bond either on the left or the right hand side of the ketone. So wherever you have the alpha carbon protons, that's the side that's going to break, okay? And so in this case at least, okay, for the iodoform test, this is what you get, all right? So not the best way to oxidize, but the product that you do end up getting is oxidized, okay, which is carboxylate. One of the most common reactions that you will find for alpha carbon chemistry is what we call the Aldol reaction. And it's also a condensation reaction. And condensation is when you do a reaction and you remove a very small molecule. Okay, and in this case, it's going to be water. All right, and so Aldol reaction is when you have an aldehyde reacting with another aldehyde in presence of a strong base. That's it. Very, very simple. Okay, so what's going to happen is that one of the aldehyde will form a nucleophile. How? Because of the alpha proton. So you form a nucleophile. Once you form a nucleophile over here with the carbon, now this nucleophile can react with another aldehyde and go for the carbon, okay, for the carbonyl carbon, which we talked about just a few minutes ago, okay, that you can do addition reactions on the carbonyl carbon. You just need a nucleophile. So in this case, what you do is you use the aldehyde to generate the nucleophile as well as the aldehyde to use as a substrate. Okay, so really what you're doing is you're using up 2 molecules of the aldehyde. So 1 molecule to generate the anion and the other one to do the addition reaction on. Okay, and so by the time you end up doing this reaction, you form a new carbon-carbon bond, which is alpha to the carbonyl carbon, and you form this new bond. You also form an alcohol group, which is coming from the aldehyde carbon, or the carbonyl. And if you remember, even when we did back in aldehydes and ketones, when we did the nucleophilic addition reactions, all of them gave us some sort of alcohol. Whether we were doing Grignard reactions or we were doing reductions, everything would give us alcohol. So here also we get that alcohol, and then you still have your ketone over there. Okay, and so the ald is coming from this ald that is left behind, and the ol is coming from this alcohol that you have just formed. This OH minus that is left behind, which is a hydroxide, can then be neutralized with water, and then you end up getting water. Okay, and so you end up losing a small molecule, and hence it's called condensation reaction. One of the characteristics about this reaction is that everything is in equilibrium, which means that you can actually reverse this reaction. Although why would you want to do that? Well, if you do want to go back, okay, so then you can. But however, for most part, you do want to go forward, okay? And so the forward reactions are called Aldol reactions, and it's a reaction between two aldehydes in presence of a strong base. Let's look at the mechanism of the reaction. It's a very straightforward, very simple mechanism. All right, the first step is when you abstract a proton from the alpha carbon. Okay, this is how you generate the nucleophile, which you already know about. That ion can of course exist as a keto or as an enol. Okay, the one that does the reaction, however, is going to be the keto form, not the enol form. All right, it's always going to be the keto form that you will take. So even if you don't write the resonance structures for me, that's fine. However, I just want you to know that they can exist as a resonance structure, but the one that's going to do the reaction as a good nucleophile is going to be this one. Okay, and so the keto form will then react as a nucleophile and attack this carbon, which then the electrons move to the oxygen from the double bond, giving you this kind of an alkoxide ion, which then will pick up a proton, okay, because once you have a base, you have water in there too, and then you end up getting this alcohol here. So it's a really very straightforward mechanism. There's really not much more to it. If you've done Grignard and if you understand Grignard reactions, this is exactly it. How you generate the nucleophile is of course through this alpha carbon chemistry, but everything else is the same thing as Grignard reaction. What happens is that once you have an alcohol though, okay, like the aldol product that you end up getting, is you can dehydrate that. So if you heat it a little bit, it will dehydrate to give an alkene. So then a water molecule is released, okay, over here. And what happens is that the alkene products are going to be a little bit more stable than the original aldol products because now you have conjugation going on. So just heating this a little bit will give you an alkene. Now, when I give this to you in a test or an assignment, you have to watch out, okay? Or even when a question is being asked of you to give an aldol product. So when you think of an aldol product, you should think of this product, okay, in which you are forming an alcohol and an aldehyde. However, if it indicates heat anywhere, then you have to take it one step further and do the dehydration, okay? And remember, when you do the dehydration, you form the more stable product, okay, which is the Zaitsev product. Always remember that. That doesn't change. And then you can do something which is called the cross-aldol reactions. Cross-aldol reactions are when you have two different aldehydes, okay, doing the reaction. So instead of taking just an acetaldehyde, you can now have, say, acetaldehyde or ethanol and propanol reacting, okay, and then you end up getting a whole bunch of products, okay. How do you get all these products? Well, the way you get all these products is because now you have two alpha protons. One alpha proton is over here and one alpha proton is over here. So the hydroxide can then go for this proton or this proton. It's not selective because both of these protons have equal amount of acidity. If the pKs were different, then it would be a different situation, but the pKs are almost the same, so the hydroxide can go for either of these. You should practice the mechanism of this one and see if you can write out all of these products. So start with acetaldehyde and then react that acetaldehyde with another aldehyde, and then try to use the same thing with the propanol, abstract the propanol, and then use the propanol to react it with another propanol. This is what you will end up getting. And then an acetaldehyde with the propanol, and then the propanol with the acetaldehyde. So, you know, try all these different combinations and see if you can get all of these products and write the mechanism of this, okay? But anyhow, when you do cross-aldol reactions, this is a big problem that you can end up getting 4 products. But you can control this reaction. So how do you control it? Think about it. How do you control this reaction? What if you wanted only this product? Well, if you just wanted the 2 aldehydes or the 2 propanols, then you will not use the other one, okay? But if you wanted a cross-aldol reaction, if you did want one ethanol and 1 propanol molecule to react, say, to give you 3-hydroxy-2-methylbutanol, how do you control this reaction? Okay, so think about that. We will talk about it in class. And then there is something called the Claisen-Schmidt reaction. Claisen-Schmidt reaction is also it's the same thing as the Aldol reaction. The only difference here is that you're reacting an aldehyde and a ketone. Okay, so instead of doing a cross aldol, which would be taking two different aldehyde molecules, now you're taking an aldehyde and a ketone, and again in presence of a strong base. Okay, so this is kind of like this, okay, where you have an aldehyde, okay, and then here's the ketone. Now in this case, you really are playing it safe, okay, playing it safe in the sense that in your aldehyde, there is no alpha carbon that has the proton, and in case of the ketone, both of your alpha carbons are exactly the same. So whether you abstract the proton from here or here, you will get only one product, okay. So this is what we call playing it safe, is where you don't really have many chances, okay, of forming a different kind of a product. So the same thing goes over here in the second combination where you have benzaldehyde and then acetophenone. You really don't have very many chances of having many products here, okay. And so you can control the reaction also, but this is a nice way to control it if you are a little bit flexible about what kind of an aldol product you want. So you can control it, okay, by selecting compounds that don't have very many alpha carbon. So aldehyde here, for example, in both of these cases, they don't have the alpha carbon. So you limit your number of products that you will get, okay, in there. Again, you can do the dehydration, okay, and you will end up getting the double bonds in there also. So instead of getting the aldol as in the alcohol will go ahead and dehydrate to give you an alkene, okay, in here. You should try and write the mechanism, okay, for both of these reactions, or at least one of them, to see if you get them. It's the same kind of a thing. Abstract a proton. Once you form the carbon anion, attack that over here, and then go ahead and protonate and then dehydrate. The interesting thing about aldol reaction is that because it's between a functional group like an aldehyde and an aldehyde, if you have two aldehydes or an aldehyde or a ketone in the same compound, you can have a cyclization going on, okay, and so you can form ring structures, which really leads to very interesting reactions then, okay. Is that if you have two functional groups, two of the carbonyl functional groups in the same compound, you will end up forming a ring structure, okay, because you'll have internal aldol going on. And so here is the mechanism of that aldol reaction going on. I don't have to go through it step by step because you know exactly what is happening with the alpha proton and then the nucleophilic attack and so on, and then you end up getting the alkene, okay. The dehydration does happen. One thing you have to watch out for when you do the cyclizations, okay, is that the reaction will occur preferentially at the less sterically hindered carbonyl, all right. So the carbonyl here that is less sterically hindered is the aldehyde, okay. So this carbon here is more sterically hindered. So obviously if you're going to do an attack on the carbon, it has to be available. So this is the carbon that is available, all right. So this is where you will have the nucleophilic addition, okay. The other thing is you have two carbons over here that are alpha carbons, this one and then this one on either side of the carbonyl. So then you have to decide which alpha proton am I going to take, okay. Am I going to take this one or am I going to take this one? And then you have to decide that what kind of a ring you're going to form, because if you take away this proton, then this carbon is going to be attacking this carbon, which means that you may end up actually forming a 7-membered ring. So remember from your organic 1 and cyclic compounds is that 5-membered ring and 6-membered rings are the most stable rings. You don't want something smaller than that. You can form something smaller only when there is no other option, okay. So you can form a 4-membered ring only when you have no other option, but otherwise try to stick with 5-membered rings or 6-membered rings. Those are the most stable rings possible, okay, in organic chemistry. So that is how you would decide whether you'll have this carbon or this carbon, okay, that will form the ring. Retrosynthesis. This is the most interesting part also, okay, for aldol reactions, and this is really how I will give you a lot of the synthesis to do. I can give you the forward one also, okay, but the retro is more fun to do because once you have the product, then you have to figure out how to make it, okay. So the thing about aldol you have to remember is you have to start from 2 molecules unless you have a ring structure, in which case there's only one, okay, but otherwise you really have to break it, okay, apart into two. So if this is the aldol product that is given to you, okay, something like this, or an alkene product, and I ask you, how was this made using aldol reaction? Okay, then you have to think about, okay, how am I going to break it? So the first thing you do is you identify your carbonyl carbon. Okay, once you look at the carbonyl, then you look at the alpha carbon. Okay, this is the alpha carbon. As soon as you see the alpha carbon, okay, over here also, then you know, aha, this is the new bond that I formed, okay, during the aldol reaction. So this is the one that I have to break. So this is the new bond. So once you find the new bond, then that's the one you're going to break. All right, here's your alpha carbon and here's your new bond. All right, so that's what you end up breaking, and once you break that, these are the two components that you will end up getting. All right, whatever has the alcohol will end up getting the carbonyl, because that's the carbon which got attacked by the nucleophile, so it will get the carbonyl, and whatever is remaining on the other side will get the hydrogen. Okay, and so really the best way to start looking for where to break the bonds is to look for your carbonyl first, okay, and then look at the alpha carbon, and then you break it apart. So what do you do with this reaction? Okay, first of all, it's a very interesting reaction simply because you're forming a carbon-carbon bond. Okay, that is the most interesting part, because carbon-carbon bonds are not really the most easiest to make, and it's a very good way to elongate your carbons, add more carbons to your compounds. And then the other thing is that, of course, you've also generated a new functional group. You've created alcohol, which is a very versatile functional group, and then if you dehydrate that, then you get an alkene. Okay, and so alkene is also a most versatile functional group. You can do any number of addition reactions and get so many different kind of products from there. So the two advantages really are about elongating your compound, or making your compound bigger by forming a carbon-carbon bond, and then of course generating a new functional group. You may not do anything with the functional group. It depends what you want, what you're trying to do. But the thing is that you can go on with the aldol product to do more chemistry. Okay, so depending on which textbook you have for the semester, you can see in your textbook, you'll have some examples in there, and we'll do some more in class also. The last one that I want to talk about, a reaction, and this is not for aldehydes and ketones. This is a Claisen reaction, and the Claisen reaction has to do with carboxylic esters. Okay, and so carboxylic esters will react the same way as aldehydes and ketones, which means that they also have the alpha proton in there. The only difference is that in the case of esters, you lose some compound. Okay, you lose a little fragment. You actually have a loss of an ethoxide. Okay, so which means that when you do the addition reaction, it's not exactly addition, it's actually a substitution. Okay, so once this carbon will add on over here, the OET, the ethoxide, is going to leave. Okay, and once that ethoxide leaves, it leaves as alcohol. Then eventually it will get protonated using a weak acid, and you will end up getting alcohol. So when you look at the product, okay, from Claisen reactions using two esters, then you will see only one ester. You do not see the other ester, okay, in there. For the aldehydes and ketone reactions, you also saw only one carbonyl. You did not see the other one. The other one was the alcohol or a double bond, all right? And in this case, you will see only one ester. The other ester part is gone. Okay, so you're ending up with one ketone. So what this does is, of course, it gives you a whole other type of chemistry where now you are reacting esters, and in your product you have an ester and a carbonyl. So it really makes for a whole other type of chemistry and whole other type of reactions you can do. So now that you have ketones here, you can form an alcohol, you can do any kinds of Wittig reaction, whatever you want to do, okay, on the carbonyl here. So it's really a similar reaction, just with slightly different twist to it. Okay, and these are called Claisen reactions. And again, if you were to do a retro on this, you would look for the ester. So this is a little bit easier than aldehydes and ketones. So once you look for your ester, then you look for your alpha carbon, and you know that that's the one that is doing the attacking. So that's the new bond that is formed between the carbonyl and the alpha carbon. Okay, so look for your ester. That is how you will start. So here are some of the key concepts that you need to know for this chapter. Is you need to understand the alpha protons, which are going to be the acidic protons. I need you to be able to compare two protons and tell me which one is going to be more acidic than the others. You need to be able to identify the keto-enol tautomers. If I give you 2 or 3 resonance structures, you should be able to tell me. You should also be able to write the keto-enol tautomerism. Substitution reactions, you should be able to do those. So whether it's using alkyl halides or whether it is using halogens, you should be able to do those 2 substitution reactions. And then of course the aldol reactions, you got to master that because that's the main part of this chapter. So aldol reactions, cross aldol reactions, and then the 2 aldehydes reactions, the Claisen-Schmidt reaction, and then the intramolecular cyclization. Okay, regarding the last reaction that we did with the esters forming beta keto esters, if you are not able to do that, it's okay. You may not be penalized because there might be only one question in there, although you should still practice it. Okay, but aldol reaction you definitely must do because I will definitely give you a question on that.